Hello, I'm Oleksii Kudryk. I'm a student of Vinnitsa National Technical University. The topic of work is intelligent information system for predicting chemicals with interactive possibilities. I will report the presentation with my colleague Yuliia Oleksii. She will start the report of chemical part and I will continue.
Hello. Currently, compounds of rare earth elements with tetrahedral oxoanions, phosphates, vanadates, silicates, arsenates are being intensively studied. This is due to their use in the manufacture of materials for phosphors, lasers, LEDs, displays, tomographs, and for disposal of various radioactive wastes, including nuclear reactors and dismantled nuclear weapons, as the service life of aluminum phosphate or borosilicate glass used for this purpose is only up to 30–40 years. The purpose of study is to develop a model and intelligent information system for predicting chemicals with interactive possibilities, which provides data reliability, high speed, and ease of operation. There are two ways to predict the limits of substitutions that are interest to material scientists. First, by experimental studies. However, this will require the cost of expensive reagents, equipment, and will significantly increase the duration of research. Second, by calculation methods that do not demand big expenses of means and time. For this purpose, we have created a program for predicting the limits of substitution by the crystal chemical method in systems with isostructural components in the approximation of regular solutions. The main task of the method is to determine the mixing energy of the components Q, the knowledge of which allows Baker equation setting the decay temperature, stability, to calculate the equilibrium composition of the solid solution X, or for a given X to calculate decay temperature. The scientific novelty of the model is that the mathematical model for predicting the phase stability of solid solution has been improved, which in contrast to the well-known Urusov model calculates the exact rather than the general critical decomposition temperature in terms of the approximation of regular solutions.
So, before the system can work, it must be filled with data. Data for this system were taken from various scientific sources, both modern and fundamental, which were published in 1930 to 1970. The data set is very large, because for each lanthonide it's necessary to enter a number of parameters that are necessary for prediction. You must also enter parameters for each type of system. Oracle products were used in development of the information system. In general, Oracle is needed to store and process large data sets and has many features that will be needed to quickly calculate a mathematical model, so it's fully suitable for this task. This slide provides an interface for predicting existing systems. First, you need to select the structure required by the existing system, the lanthonide, variable, and the step. Then click button Calculate. After calculation, we receive the diagram on which it's possible to predict limits of substitutions or critical temperature and the table with calculations. This slide provides an interface for predicting any system. First, you need to select the structure, required constant lanthonide, variable lanthonide, anion, and step, and then click button Calculate. After calculation, we receive the diagram on which it's possible to predict limits of substitutions or critical temperature and the table with calculations. To calculate the limits of substitutions, decomposition temperature, and assess the stability of solid solutions, it's necessary to know the parameters of interaction, mixing energy, of solid solutions. There are several theoretical and experimental methods for determining them. During the period 2007 to 2070. They are very repeatedly used to calculate the interaction parameters in phosphate systems, comparing our results with previously known calculations for europium and gadolinium. We can conclude that our mathematical model is reliable, and the information system created by us provides quite accurate results for such systems. On this slide, you can see an example for interface entering thermodynamic systems and elements that apply for each respectively. Here you can see the basic applied EIR database model. Here selected the main tables of this application area, which stores the data required for calculations, like atom length, sum atom length, volume cell, structure solid, and term system. So developed intelligent information systems that reliable, appropriate, ambulance, convenient, effective, and universal for practical use by material scientists. So scientific and technical results of study are: for the first time, intelligent information system for predicting chemicals with interactive possibilities was created. The knowledge base is based on advanced mathematical model of prediction, which allows to increase the accuracy of mixing energy calculation and calculate accurate rather than total critical decomposition temperature. Through the application of JavaScript, HTML, PLSQL technology, such functions of the system and as providing remote access to work with the system includes the storage of initial data, visualization of predict results have been software implemented and experimentally tested. Thus, based on the study and construction of easy operate IIS, the accuracy of predicting the phase stability of solid solutions increased. At the same time, the created IIS allowed to abandon experiments which dramatically increased the speed of forecasting and several orders of magnitude. Through the application of JavaScript, HTML, PLSQL technologies, such functions of the systems as providing remote access to work with the system, input and storage initial data, visualization of predicting results have been software implemented and experimentally tested. Thank you for your attention.